We are still on ladder and hill problems. So let's see how we handle this. Okay. The diagram below shows a uniform wooden rod AB of mass 70D. Not here, the word uniform, it means that the weight is going to occur in the middle, or the center of gravity is in the middle of that rod. And length 5 meters. The end A rests on a rough horizontal ground. Remember here the word rough, it means that we're going to expect some friction. The rod is in contact with the top of a rough bed of height 2.2 meters at C, with SC equaling to 3.5. So if it's 3.5 from here up here, this is 1.5 because the hole is 5 meters. Given that the constant of friction on the ground is 0.6 and the rod is above slip, find the angle rod makes with the horizontal. Normal reaction at A and C, then coefficient of friction at C. So we start by putting, I think you see this is my A, this is my B, this is 1.5. Because this is a uniform rod, we expect that the weight is going to occur in the middle. So this is, let me assume this is going to be my middle. So the weight is going to be there. The weight here is 70, these are the kilograms, I'm applying it with D. I'm going to be adding 70, then times B. Okay, now if that is 70 times, it means from here to here, there is 3.5. But because this is in the middle, it means that from here up to here, from here up to here, it's going to be 2.5 because the weight is acting in the middle. But because this is 3.5, it means that this is going to be 1 meter. Then this balance from here up to here, it will be the 1.5, and when you add that, you will get our 5. Okay. Now, else the reading axis is at some force, because there is a contact here, we expect a reaction. So this is going to be reaction at A, and here we're going also to expect a reaction because there is contact. So here we are going to have our reaction at C. Okay. So this one, of course, it was rough. So when this is above slip, it means that this one is going to move this side. So friction is going to be that side. So here I'm going to be having my friction. And remember, friction is given by the coefficient of friction, but at the ground, it has that is 0.6. Then times the reaction there, which is the reaction at A. Then here, because it's going, when it slips, it's going to be coming this side, then friction is going to oppose in this order. So friction is going to be that side. It's going to be, we don't know this friction, but let us call it mu RC, the friction at C. This one at C there. So we are almost there. What are you missing? I think everything is almost there. Okay, we know from here up to here is the 3.5. So basically, of course, reaction is always perpendicular to that point where it is. So basically, that's what we have so far in the equation. Now, after that, now we can come and then get the angle that the rod, this rod AB, makes with the horizontal. This is our angle, theta. So it's that we have this, and we have from here up to here. Remember, from here up to here, there is, from there is 3.5 meters up to that point there. So it means that now I have the hypotenuse, I have the opposite. So meaning there I'm going to use sine. So my sine theta is going to be the opposite. That's 2 over 3.5. So from there, my theta is going to be submitting that 8.94 degrees. That is the angle the rod makes with the horizontal. B, let us get reaction at they want us to the reaction at C. Now reaction at C, reaction at A and C. So if we want reaction at C, we can first take now moments from here. If we take moments from there, means that now all of forces that are coming out of this are going to be zero. So if we take reaction moments at A, it means that we are going to get this reaction at C. And when we want reaction at A, we shall take moments at C. But be careful there. Okay. So let me say taking moments at A. We are going to take them anti-clockwise. So here, be careful. I have this so that you can see where the things are going to. If I'm taking moments at A, you see that this one is going to go anti-clockwise. Now, the perpendicular distance from A to this, I think this is going to be, this is the perpendicular distance from here to here. So I'm going to be having now RC times from this is the perpendicular distance from A, where I'm taking, remember moment is given by the product of the perpendicular distance from the point where I take moments times the force. Now this is our force. The perpendicular distance from here up to here is 3.5. So 3.5. That's I think it's the only anti-clockwise moment. Now we are using the principle of moment, which says the sum of anti-clockwise moments should be equal to the sum of clockwise moments. Now what do we have in the clockwise moments? So it's that this force here is from here, the line of action is at this point. So this moment is going to be 0, this is going to be 0, and this is going to be 0. So what we are left with is going to be only, I think we can see from here, this is the only force that is going to survive the weight. So it's acting in this direction. I think you see, for it is acting clockwise. So I'm going to get 70 G. Then times its perpendicular distance from A. Now the perpendicular distance from A of this, from here up to here, I think you see, this is my force. So the perpendicular distance from A is here up to here. So if I draw that simple triangle here, so that we can get that distance. So this one you see, this one is theta. I think you can see that is theta. So now from here up to here is 2.5. Now I'm interested in getting from here up to here. So what is going to be? So this is adjacent, this is opposite, this is going to be 2.5, then cos theta. So now it means from here up to here is that. So I'm going to say 2.5 cos theta. So basically that's what we have. Then the other thing is, now we are going to divide it through. We have our theta is there, or you can say you don't, by the way, you don't have it. So you can just say, and then you put in our theta there. So our RC from here is going to be 70 times 9.8 times 2.5, then cos our theta 38.94 divided by 3.5. So our RC from there is going to be, press my calculator. So me here I'm getting 381.1242 newtons. So that's my reaction at C. So after that, now I want to get my reaction at A. So take reaction at A, now I'm going to take moments at C. So taking moments at C, where should we take? Clockwise, because this force is going to act clockwise like this. Take moments at C, clockwise. Now what do we have? Now, you see when I take moments at C, any force from C is going, its moment is going to be 0. So this is going to be 0, its moment is going to be 0, this moment is going to be 0. So I have, well, how many forces surviving? This is surviving, this is surviving, and this is surviving. So taking moments at C, it means that I have first of all RA times what's the perpendicular distance of RA from C. I think now there you can see from C this is going to be, so I can able draw that. That's going to be the perpendicular distance, of course, as you can see. So this is going to be my perpendicular from there. So it means that now you know from this arm is the same as this arm here. this angle here is going to be theta. So if I have this angle, remember, we have from here up to here is 3.5. So if this is theta, then this is theta. This one, the perpendicular distance from here, I think you can see. From here, this is the force. So force is going to act clockwise. So the perpendicular distance, I think we see from C to this is the perpendicular distance. So if I have this as theta, it means that now, and I have this hypotenuse at 3.5, so this is going to be my adjacent. Adjacent to this angle, so this is going to be now 3.5, then this is adjacent cos theta. Simple as that. So I have this because the perpendicular distance, this is a vertical force, its perpendicular has to be horizontal. So that is 3.5 cos theta. I think that's the only clockwise force I have. I think it's clockwise. Now, this one here from C, I think we see this one is going to act in this order, which is also, I think this one is also clockwise. This one is clockwise, sorry. My joke is, this one is clockwise. Then when you look at this, you see what we are going to be having. This one is going to act anti-clockwise, and also this one is going to act anti-clockwise. So, I come at this. This is going to be equal to 0.6 RA times its perpendicular distance from C. I think we see, if I have this from here up here, the perpendicular distance from here up here is this, for this force here. So, from this the perpendicular distance, I think we can see from here up here, because this is horizontal, its perpendicular distance is vertical. 2.2, then plus, now I have this one, the 70 degree times its perpendicular distance from C. Now, this one I think you can see, its perpendicular distance from C is going to be this here. I think you see this perpendicular distance here from C. So because we have from here as, let me draw it, I think you can see it here. Let me draw that diagram there. Then we can draw it near here. I think you see this is theta. So we have this as 1 meter. So it means that now I need the distance from here up to here. I think we can see it's adjacent. It's going to be 1 cos theta meter. So minus 1 cos theta. Then beside the RA. So I take everything beside and I factorize out RA. So when I take this, when I take this side, I'm going to be having RA into, here I've been remaining with 3.5 cos 38.94. Then minus, when I take this side, you see when I multiply 0.6 times 2.2, I get 1.32. It's going to be giving me 70 times 9.8 times cos this angle is 38.94. If I write that now, my RA is going to be 70 times 9.8. Over this one is going to give us, okay, let me just put it here once. So here, my RA, barrier I get is going to be here I'm getting 380.4948 Newton. So that's my reaction at A. So after having that, then let me come to part C, where they want me to get the coefficient of friction at C. Now, to get the coefficient of friction at C, it means that now we need to resolve this force here, this friction here. We are going to resolve this into the vertical and then the horizontal component. Okay. Of course, you see, if I have this here, this angle here is going to be theta. So if I redraw also this one here, I think you can see. It means that if this is theta, even this is going to be theta. So now, you see, I can ably now resolve this force here. It means that if this is theta, of course, this is going to be a balance of theta, and this is going to be also theta. So, from here, if this is not our theta, it's 38.5. It means that now, this balance here is going to be 90, because this is 90 minus 38.94, which is giving me, so the whole of this is 51.06. Okay, now you can try to resolve this. When you resolve this, you see that the horizontal, this is going to be adjacent, this is going to be the hypotenuse. Or, if you want, you can take this as the 38.9 and resolve it like this, and then like this. So, let me use this angle. So, if this is the angle, this one is going to be adjacent. I think you see to this force here. This is going to be adjacent, so it's going to be mu RC, then cos 51.06. Then this one is going to be mu RC. You see, this one is going to be the opposite, sine 51.06. So now, from there, then we are going to take moments at, let me take moments now at, let me draw for you that diagram again so I can see if I take moments at, again. Okay, I think you can see this diagram. Now, we have resolved this force, so we also resolve this because this is also a force acting, so when you resolve it, RC, we get it C vertical. This way, I resolve this, and never conject it here. When we resolve C, we have this force acting in that direction. This one now, I think you can see it there. Now, RC, because this is adjacent, cos 38.94. Then its horizontal component is going to be in this direction here, which I'm going to say RC sine 38.94. So now from there, you can take moments here or here, but that one is going to be lengthened method. So now we take, resolve horizontally, because you see we have this, and these are the horizontal forces. So resolving horizontally, you still go in that direction. We have first of all mu RC sine 51.06, then plus we have this force 0.6 RA is going to be calling this the only opposing force going this side, RC sine 38.94. So it's that we have RC, this is the only thing that we need. So I put everything there. So I take this side, then I put in here my mu into now my RC, which is 38 min or 42 into sine 51.06 is going to be equal to my RC, the same 381.1242 sine 38.94. Then minus, now when I take this side, 0.6 RA. My RA is 380.4948. So from there, I can get our mu as I think you can see the answer we are getting. So this is going to be 0.0379, and that's going to be our qualification perfection at C. So that's it, members. I wish you well.